Hello students. So today we are beginning a new topic which is index form. So we are just going to do these two topics, index form and logarithms, before we move on to algebra. So a long time ago, before the invention of the computer, there were no calculators. So merchants have to keep track of very large numbers by head, and they have to do these complex calculations by head. Let's say, for example, you have a number, let's take a random number, 256 multiplied by 128. So imagine you have to calculate these numbers repeatedly every day. It was going to be a tedious task. That's why they invented these indices, so that they might be able to calculate larger numbers in a faster way. So if you take 256 and you express it maybe in index form, you try to express it in index form, 256 can give you 2 to the power 8, and this one can give you 2 to the power 7. So if you need to multiply these two, you're just going to say 2 to the power 8 multiplied by 2 to the power 7. So now you have a more simpler form of this operation thanks to index. So let's remain here. I want us to remain here and to look at the board. So index form tells you how many times a number is multiplied by itself. For example, if you have a number a to the power n, it means that a is going to multiply itself n times. So a times a times a up until it reaches n times. So a is called the base, and n is called the index or power. So when it's singular, it's called index, and when it's plural, it's called index. So for example, 8 in index form is given by 2 times 2 times 2, which is 2 to the power 3. This being the index, and this being the base, index or power. So there are laws that govern these indices so that you can perform operations on them. The first law of index says that if you take two bases, if you multiply two indices to the power m multiplied by a to the power n, our example, remember these two are multiplying. So if you take a number a to the power m multiplied by number a to the power n, you say that a to the power m plus n. So you add the powers and you take the common base. So let's do the same here. 2, 2. So we're going to have 2, 8 plus 7. So this is equals to 2 to the power 15. So you see, this is a cleaner way of doing complex calculations. You use index form. So that's why the early merchants invented index form, so that they can be able to do complex calculations. So let's look at the second law of index. Let's look at the second law of index. The second law of index states that if you have figure a to the power n divided by a to the power n, this is the second law, you are going to say a to the power m minus n. So division can appear like this, or it can appear as a to the power m divided by a to the power n. Both produce this result. Both produce this result. You take the common base and you subtract the powers. So we can use an example, 2 to the power 4 divided by 2 to the power 2. So this is going to be equal to 2 to the power 4 minus 2. This is equal to 2 to the power 2. So we can do a proof for this. 2 to the power 4, that's 16. And 2 to the power 4, that's 16. And 2 to the power 2, that's 4. So 16 divided by 4 is equal to 4. And here our answer, 2 to the power 2, is 4. So this proves that doing this index is the same as solving. So let's move on. We have talked about the first law of index, which is multiplication, and the second law of index, which is division. So the third law of index is power of a power. So if you have an index a to the power n, multiply a to the power n to the power m. So you have a to the power n to the power m. So what you are going to do here is you take the base to the power n multiplied by m. So when you have a power of a power, you multiply. So for example, if you have 5 to the power 3 here, squared, this is equals to 5 to the power 3 multiplied by 2. This is equals to 5 to the power 3 multiplied by 2. In this case, you don't add because this is to the power. And this is equals to 5 to the power 6. That's 5 to the power 6. So let's move on to the fourth law. Let's talk about the fourth law of index. It states that any base to the power 0 is equals to 1. So if you have any number to the power 0 is equals to 1. So you might have 1000 to the power 0, that's 1. Even if you have half to the power 0, that's 1. So any number to the power 0 is always equal to, let's say have a number like 256. So it's always equal to 1. So let's talk about the fifth law of index. Fifth law of index, which is the negative index. So if you have an index like a to the power minus n, this is equal to, if you have an index like a to the power n, if you have an index like a to the power n, this is related to the division index. It's related to the division index. So if you have a to the power n, this is equal to 1 over a to the power n. So there is a relationship between this negative index and division index. So if you have a number 20 to the power minus 1, this is equal to 1 over 20. That's the negative index. So let's talk about the fraction index. Fraction index, which states that the number a to the power m over n is equal to a square root of the denominator a. Square root of the denominator multiplied by the numerator. So the numerator will become the power here, the remainder is the power, and the denominator will square root. So for example, you can have 8 to the power 2 over 3. 8 to the power 2 over 3. So in this case, m is represented by 2. So this represents m, this represents n, and this represents a. We put into our formula. There. So this is equal to square root of cube root of 8. Since n is 3, so cube root of 8 squared. The cube root of 8 is 2 squared. So we first remove this side, the cube root side. So this is equals to 4. That's the fractional index. So let's talk about let's talk about the power of product. The power of product. So you might have two numbers, a and b, to the power n. This is equal to a to the power n, b to the power n. Each number is multiplied it's powered individually. Each number receives the power individually. So you might have 3ab squared. So you are going to have 3 squared multiplied by a squared multiplied by b squared. So each individual constant